We're going to start this off by inviting all of our panelists to say parallelism 3 times fast. Ready, go.
Okay. Parallelism, parallelism, parallelism.
Nice.
Yep. Parallelism, parallelism, parallelism.
Yep.
Sharding.
All right, let's talk about it. So oh, look at me now. All right. Parallelism increases throughput. Why do we even would need more throughput? What kind of, and I'm gonna ask open-ended questions in no particular order, feel free to jump in and go for it. So what are the use cases that are currently not within scope because we don't have the capacity and the throughput to achieve these use cases on-chain?
Who wants to go first?
I can go first.
Okay, you go first.
Sure. So right now, Ethereum processes about 1 million transactions per day. So it's just a really low number relative to even a single app that achieves mass user adoption. Like you can imagine an app that's #1 on the iOS store with several million daily active users, say even 1 million daily active users, 50 transactions per user per day is 50 million transactions per day, which would be 500 TPS. So we just need much more throughput than we have right now.
Sure. Yeah. I would say a lot of applications are actually fine being a single-threaded, non-parallel design, but in and of themselves, you need parallelism to expand the potential for many applications to use the same blockchain. And in that sense, parallelism opens up a lot more capability, a lot more throughput, a lot more potential for a blockchain. And so while you can and probably should design most of your apps in a single-threaded way, you need parallelism to make sure that all these applications can live and breathe the same block space. And I think for that's where parallelism is very important. And 1 million transactions a day is incredibly low for even a basic consumer-grade application. So obviously we need more throughput. We need to be able to support our applications, and that's why it's very important.
And Misha, why wouldn't we split up the underlying blockchain into something like shards to accomplish this higher throughput?
Oh, it's like first of all, the higher throughput. Let's be honest, it's not only about potential apps. It's like let's be honest that the demand comes where the liquidity is. So like it's like in our case, it's since we're effectively like L2 rollup, like this kind of thing. It's like the liquidity comes to ETH because it's the only place where the liquidity is. So effectively, the more you have the liquidity, the more you have the interest in doing random shit with it, and the more you have interest, the more you need the throughput. So that's the thing. Why do you need to split it to sharding? I mean, it's actually pretty easy. It's like at a certain point you reach the effectively data locks. Okay, you effectively reach the data blocks. It's like you try to for example, transfer like a single token 1 million times per sec, whatever times per sec, right? And you're not going to be able to do it because you're going to be required to sequence those transactions like one after another because it effectively affects just one single index in the database, right? So that's the thing. And that's basically that's by the way the reason why Solana's site also transfers of a single token are kind of being serialized, for the execution, because it's just a fundamental limitation. So to bypass this limitation, you got to do not only the execution parallelization, not only execution parallelization, but you also got to do data parallelization, data access parallelization. This introduces complexities. This introduces the necessity to do synchronization in the background, yada yada. This is a trade-off with consistency. But what the hell? It's what do we want? Do we want to go fast or not?
Okay, so we're parallelizing at multiple layers of the stack. Yeah. So let's go through them. So let's start with the execution environments, the VMs. Why are we choosing to parallelize something that isn't inherently built to get parallelized? So that question's about the EVM. Why, and this question goes to Keone, why are you choosing to parallelize the EVM and not one of these VMs or one of these languages that already has some inherent parallelization properties?
Sure. Maybe I should just start by introducing Monad. So at Monad, we believe that we must parallelize the EVM. we need much more throughput, and we also need to do it in a way that doesn't cause any compatibility problems for developers at all. So Monad is a super high performance EVM layer 1 that introduces parallel execution as well as other improvements, ultimately to deliver full bytecode compatibility and to unlock all of the performance in the hardware underlying. For Monad, Monad does optimistic parallel execution. And in just a couple of words, just to describe it very, very briefly, it is the process of running a bunch of transactions in parallel, generating a bunch of pending results, where each pending result keeps track of the inputs and the outputs for that transaction. And then Monad steps through those pending results one by one in the original order of the transactions and commits them and reschedules work whenever there's a conflict. So ultimately, this is delivering a very Ethereum-like experience with blocks in which the transactions are still linearly ordered, but then under the hood, and it's completely under the hood, so the developers and users don't have to worry at all about this. There's just strategic parallelism that ultimately gets all of that work done much more quickly than if they were just run one after the other.
Okay, you mentioned in there the optimistic parallel execution. So I'm curious how this separates from some of the existing parallel execution types. If you could unpack that a little further, and then we'll expand to the rest of the stack.
Sure. I think maybe the single most obvious thing to point out is that in Monad there's no requirement for pre-specification of dependencies. So any transaction depends on state, on particular account slot tuples within the overall Ethereum namespace. And in other models, like in Solana, in order to specify a transaction, you have to specify all of the dependencies, which can actually cause problems because sometimes when that transaction lands, it's a different set of dependencies that is actually required. And so then the execution actually fails. So with Monad, similar to Ethereum, there's no requirement for that. There's no requirement for basically access lists. And instead, just under the hood, Monad is figuring that out, running transactions in parallel, surfacing all of their dependencies, pulling all of those state dependencies from the SSD into RAM, and then generating a pending result, and then stepping through the pending results and committing them. And one really awesome thing about this actually is that because all these dependencies have been surfaced and pulled into RAM, if there is a re-execution that's needed, then that re-execution is actually very fast.
Is this a property that's inherent to the EVM? And I want to loop in Nick and another parallel execution type and contrast this with the rationale behind not choosing to parallelize the EVM and instead going with Sway and the Rollup OS.
Yeah, so unlike this approach where you're kind of taking the EVM and you're kind of saying, okay, well, we'll pipeline a bunch of this stuff in a different way, and then we'll parallelize it over time based upon what everything is going to touch. With the Fuel VM, we do things very, very differently. So for us, we do explicitly say at the transaction level, we're going to touch these things. So we use UTXOs to define what areas of state that we're going to touch, and then it makes it extremely trivial for a machine to look at these transactions touch this area of state, these transactions touch this area of state, and then you can process all the transactions in one go. The main motivation for us not using the EVM is that I've been using the EVM a very long time, almost since it started. So almost since Ethereum wasn't a thing. And I have to say that it's been both very nice to have in many senses, but also a incredibly challenging environment to develop anything of any level of sophistication. So basically, the need for us, or the want, or the desire to have a better virtual machine for Ethereum really came out of the fact that the EVM is so heavily constrained by virtue of its design itself that even introducing parallelism or other things into it, it's not enough. Like, it's just quite frankly not enough. And so for us, we really feel like, we want to approach the problem and say, we don't care about the business logic of reusing the EVM. There's a bunch of teams that are going to do EVM stuff. They can go do EVM stuff. For us, we want to do something different. We want to really genuinely fix these problems at a different level in a different way. And as well for things like, the way that Ethereum works, like we've already addressed things like where if you make a state access list, for example, and things change within that state access list, like our model is very flexible to adapt to that because we understand how Ethereum works and we understand that you want to have Uniswap be possible, when you're signing transactions, you don't know the state of things, you want things to progress in that way. So for us, it's very much that like we think Ethereum really needs a new environment and it needs something really fresh. And I think that while I'm grateful that there's people trying to make the EVM really performant, that's fantastic. For us, we just take a very different approach. Yeah.
And Misha, you take an entirely different approach, which is sharding. And yeah, I'm curious to hear your take when it comes to the sharding approach and not the parallel approach. I have a feeling these are quite similar in practice, but could you explain a little bit more behind the reason for sharding?
Yeah, I mean, in fact, the whole sharding thing is like parallel execution over EVM. That is true. It's like what are like advantages and disadvantages of that, like in comparison to trying to figure out things on the virtual machine level, right? It's like advantages of that is that you get deterministic execution. It's like anything that you have submitted, it's gonna be there. It's like there's no optimistic assumptions or anything. It's just gonna be there. So that's the thing. There are corner cases, like if you touch a lot of shards, and that's gonna be trouble. But that depends. It's like in general, if you work with if you work with an application which is built for parallel execution on top of sharding, then I mean, sure. I mean, it's like you're gonna get everything executed deterministically. That's the first thing. Second thing is sharded execution environment effectively is what easily and pretty organically connects to the currently existing ETH. I mean, we effectively work with ETH just with one of our shards. So I mean, that's what we call a ZK sharding, not just ZK rollup or something. It's like we go with ZK sharding because we want to be composable with ETH, because we want for people to be able to work with ETH just with our shard, just like with our shard. So it's like to tap into that whatever amount of liquidity they have right now. It's like to do, let's say quotes, all right? Quotes flash, not really flash actually, but with tricks, but flash loans with the ETH liquidity from L2, this kind of tricks. It's like, that's the point. Disadvantages of that is, I kind of mentioned that briefly already, is cross-shard communication is a very complex thing. And let's be honest, even I would say theoretically, it's not resolved in all the cases. So we have to do sometimes, don't do this, please user, don't do this. It's like, it's probably gonna end up bad for you. So a little bit more complexity gets on the developer's shoulders if they're actually trying to employ all the parallelism we can provide. So that's the thing.
Okay, are we recreating a problem here? The interop problem? Once we split up execution into multiple threads or multiple shards, are we recreating this interop problem across shards or across threads?
Okay, here goes a take. It's like effectively, it's not just interop problem. It's more like a state fragmentation problem. But what I'm trying to say is that state fragmentation problem is not an interop problem. It's a scaling problem. So that's like the take, all right? So, and effectively, to avoid all of these interop problems, I mean, we effectively bake in the sequencer under each shard. It's like which makes it kind of composable, which makes each shard composable with each other. So that plays the trick. That does the trick, I would say.
For fuel, no.
No, there's no interop problem for fuel.
No.
Okay, and Monad?
No, everything in Monad is, I think the overall goal is to make it really simple for users and developers. We do that by handling the complexity under the hood, introducing the optimistic parallel execution. Another thing I didn't mention was parallel state access, because something that you might or might not know about Ethereum transactions, the work is generally IO bound, not CPU bound. The total amount of like computation being done in these transactions is actually very small. It's like addition, multiplication, you know, SHA-3. Like these are pretty, they're not expensive from a compute perspective, but what is actually expensive is reading the state dependencies from SSD. But SSDs, modern SSDs are actually pretty powerful things. You could think of it as a bottle with a wide bottleneck. It's got a lot of bandwidth, but we need software that can effectively utilize all of that bandwidth. So for example, and I'm sorry for the tangent, I'll wrap up in a sec, but you know, a high quality SSD costs about $200, has 2 terabytes of capacity, and can deliver 1 million I/O operations per second. So that's a lot of bandwidth, but you need software that can actually utilize all that bandwidth and access state in parallel. So with Monad, another thing that we've done is make the parallel execution performant by building a custom state database that can utilize all this bandwidth on the SSD. So parallel state access, thus enabling parallel execution.
But I thought we were here to replace databases with blockchains. What is this database that is very important to parallelize?
They're not very different. Here goes a surprise to you.
Yeah, I mean, ultimately, blockchains really are databases in some sense. They're just decentralized databases with, in most cases, I guess with the exception of sharded blockchains, but in most cases, a distributed database where every node is a complete replica of all of the state. And we're enabling shared global state. You know, for example, like Aave, there are millions of accounts on Aave. Literally every node has information about all of those depositors, all of their balances, all of their everything. Everything is being maintained. So it really is a database, and in order to make this database performant, we need, under the hood, a custom database that can store this Merkle tree data really efficiently.
Got it. Okay. So this is all the execution, the committing the state changes to this ledger. Now, Misha, you mentioned there's another layer that also we parallelize underneath this execution. Could we dive deeper into the stack and talk more about the rest of the paralleled environments?
So it's like, yeah, it's like just again this like this example. With this example, it's like why just besides the execution, it makes sense to parallelize also the state access. All right. It's like again, it's like what happens. So it's like just guys answer me. What happens if, for example, like within your systems, a user tries to like transfer like a single token 1 million times? It's like, is it going to be parallelized? It's like most probably not, because it's the single index if an application is not designed that way, so it could be parallelized, right? So if it's designed that way, it's going to be parallelized in your systems.
Yeah, so in Monad, for example, that would not be parallelized. That would be executed serially.
Yeah.
However, it would be very cheap to execute serially because it's reusing the same pieces of state, and that state is in RAM. And RAM is very cheap. Like you can access RAM, like read something in about 100 nanoseconds.
Okay. So I mean, effectively, it's like the primary bottleneck of like those clusters, effectively, which we're working on top. It's like those clusters are how to translate this? It's like they have a very definitive replication interval. So this makes them. This makes those replication intervals effectively ticks. Right? It's like ticks of a cluster. So the whole user experience of like interacting with these clusters, with all of these like blockchains, right? It's all about waiting for the next tick. It's not about waiting for the node or like software to like respond to that. It's like effectively, so that's why you can, for example, run ETH on your phone. It's like because it's not about the performance of the software. It's about it's about the frequency of those ticks. So, and the people and effectively users, they estimate the performance of whatever cluster there is by the frequency of the ticks. It's like the more frequent ticks are, the better the thing, like according to their opinion, right? So effectively, when we're talking about, and those ticks, it's like if you stumbled upon, for example, a block on the data level, like for example at some token, you stumbled upon it like within the single tick, then you gotta wait to another one to do something like, to do something around it if the transaction didn't came in time. If it came in time, you will pack it into a single replication packet until a certain limit. You're gonna be required to wait for a next tick and do a thing over a next tick. So parallelizing the data axis effectively also solves, this kind of thing. It kind of turns the whole system into a large trustless map reduce.
Wait, sorry. So if I understand what you're saying that because inherently some things are serial, you want the fact that there's a bunch of shards, these shards to be able to like do work in parallel, because inherently some things are going to be serial within that shard, but then they're parallel across different shards.
Yeah.
And then how frequent are the ticks?
I mean, it's like it depends. It's like we're experimenting with half a second ticks. It's like on a shard. It's quite large, but half a second is, it's reasonable.
So I would just say from the perspective of Fuel and what we were trying to do with our virtual machine design in respect to these kinds of things, I think the first thing is I/O is definitely the constraining factor. So we can definitely optimize a lot of other aspects of execution, but the drive, going back and forth to that hard drive, is like the worst thing. It takes up most of the resources. So the thing is, when you have a system that was designed, like I was around close to the time when we were discussing the EVM and trying to get rid of the EVM, like around DevCon 1, there was quite a few discussions after it had been implemented that we want to get rid of it. We didn't. Basically, that it was very drive heavy because the EVM has this giant Merkle tree that captures all of the state. And this particular Merkle tree is a real pain when you're processing the blockchain, because every time you change the state, like any state element, you have to go all the way up, 256 steps, all the way up to the top of this Merkle tree. And then literally every single time, and for one ERC20 transfer, you have to do this like every single time, twice, maybe even 3 times sometimes. Reading is just a read, but actually writing and updating is this immense amount of work. So with Fuel, when we designed it knowing all of these constraints in mind. We knew these were issues, like big issues with the EVM construction. So for us, we realized that using a UTXO model allows us to get rid of the state tree altogether. We don't even need it. The state can remain true. All of the atomic processing can happen over the different sets of UTXOs. And everything gets processed in parallel where it can be. Obviously, there's times when things are processed in serial because 2 things touch the same area of state, or in our case, the same smart contract. So those need to be processed in serial. But everything else can be processed in parallel. And inherently, we get to have the advantage of looking back at the EVM and sort of the mistakes that were made there, and to say, hey, like, we can do this a lot better. We can do something really different here that is both as secure, it's as safe. It has the properties of parallelism, but it also just addresses some of these like key underlying constraints. So for us, this was like a big motivation for even doing our own virtual machine in the first place. Yeah.
Well, I would just wanted to say one thing, like regarding the Merkle tree, there are a lot of opportunities to update the Merkle tree more efficiently. And you can recalculate the Merkle root in parallel. That's one property of it, is that if there are different parts of the tree that need to be updated at the same time at the end of the block, there actually is a lot of opportunity for algorithmic improvement. So I would actually disagree with you on the, like the badness of the Merkle tree. I would say it's more just an algorithm right now that maybe is not very efficient in like Go Ethereum.
Well, we'll agree to disagree, because it's pretty horrible processing I would never want to do if I don't need to do it at all. And not just that, but there's another thing which is very, very important to our design, especially over the EVM design, which is that we knew state was a problem from the beginning. So we knew that drive time was going to be an issue. So what we did was we said, how do we give the developer many different ways to use bandwidth instead of state? So use bandwidth over the wire bytes instead of going to the drive. And so Fuel is armed with a lot of different ways for the developer to not touch the drive as much as possible, because we know this is an actual issue. And so this is the advantage of looking back on previous designs. We can say, hey, wait a second, here's a huge opportunity. It's not just getting rid of the global state tree. It's using more bandwidth, it's using other tools that we have at our disposal to move the physics over to something that we know we can really process well. So I would agree to disagree in this case.
Is this a disagreement about the UTXO versus the account model? And this is the...
I think it's a disagreement about the heaviness of processing that comes with having a global state tree. And I think that I'm sure there's ways you can pipeline that kind of stuff and you can make that more efficient. But if you don't need to do it at all, and state still retains the same level of verification, the same level of truth, then you've got a huge opportunity to remove that if you can, in my view. But mind you, Fuel VM is not used yet. The EVM is very used. So there's 100% a very reasonable case to make the EVM more efficient. It makes absolute sense to do this. But I'm just saying that, you know, in our case, we get to look back on it and we get to do a different kind of design.
Yeah, I think we're clearly solving very different problems, which is great because we need different teams to imagine very different things and produce a result that solves problems for developers.
It's a benefit to the market. So, you know, us and more crazy infighting over these very nuanced design choices will be very good for everybody using blockchain, you know, 10 years from now. So as much as we disagree, it's actually very, very good and fruitful that we do disagree and that we're trying different things, I think.
Optionality is critical. So could you describe why it's important to build on the EVM, or why someone would build on the EVM, and why someone might build on the Fuel VM, since they solve two very different circumstances?
Yeah, sure thing. I think there's a couple of major reasons. The first one is that realistically, almost all developers of decentralized apps right now are building in Solidity, or in some cases Viper, which compile down to EVM. So there's very much a network effect of developers, libraries, tooling. We have great tools like Foundry and Hardhat. And also a very robust research community that's doing a lot of applied cryptography research in the context of the EVM. So it's really the dominant standard. Right now, about 97% of all TVL on-chain is in EVM applications. And it's just a really strong network effect. And so it's useful to a lot of developers to basically not have a vendor lock-in problem where they've built for one specific environment, where then it's really hard for them to move to another environment, which we see in certain cases, like with the Solana developers who built for Solana and then found like, oh, I can't move my application anywhere else. So basically making the EVM very performant gives developers the best of both worlds between portability and performance.
Yeah, I would say for us, it's a slightly different kind of calculation. So my whole thing is I've been using the EVM and I've been using Solidity for a very, very long time. So I know what I'm working with. And quite frankly, I don't like it. It's been horrible. It's been horrible for many, many years. And I've built a lot of things with these tools. And I think that I love them in many ways. I love Solidity, and I love the fact that the community's done what it's done with both Solidity and with the EVM. We've pushed it to such an incredible extreme for what it is, and everyone's gotten tremendous value out of that. But at the same time, at this stage and at this juncture, in 2024, I'm sort of ready to try something else. And so for me, Fuel and what we do with the Fuel VM and Sway is very much to try to alleviate this feeling that you get when you write something in Solidity, and we talked about this in the last panel, you just feel very uncomfortable with what you've written. And yes, there's lots of tooling and lots of stuff, but you feel quite uncomfortable. And then you do all kinds of weird things because the EVM is designed a certain way. And you go, man, this just doesn't feel intuitive at all. It doesn't make any sense for what we're actually using it for. And that's because the EVM was designed very quickly. It was designed in a rapid pace, and it got us very far. But now we get to look back on it, and we get to try new things with rollups, with new execution layers, with new kinds of modularity. And so for us, because we can try something new, we can do all kinds of new exciting things that fix a lot of these problems. And you know, for us, that's the exciting thing of rollups and the exciting thing of doing something new. So for me, it comes from a feeling of just being horribly unsatisfied and wanting to satisfy that with something that feels right, that feels solid, and that feels safe. Yeah.
Nick, what would be an example of something that you think is horrifying in Solidity development?
Well, where do we start? Let me see. So the first thing is Like when the DAO hack happened, and it was a reentrancy bug, like the first big one, you know? There was maybe like 5 people who really knew what reentrancy was for the EVM, and we could have designed something for that to restrain that property, but because it was sort of new territory and really only Gavin had tests for it and whatever, we basically had a weird situation where we had something that is technically a feature, but is also actually a horrifying feature used incorrectly. And that was just sitting there, like by design. It was just around, right? And there's many, many of these within the EVM itself. So self-destruct is another one. There's a lot of crazy side effects there. There's a lot of crazy side effects to the way constructors work, for example. Auditors have learned to understand this incredibly odd machine we call the EVM, but it has not been a fun experience by any means. And while it is better understood now, to this day, there are still reentrancy bugs. There are still incredible vulnerabilities that are being created all the time because of the way the EVM and the way that Solidity works. And so I would just say, for me, it's like, I can give you like a massive laundry list of things I would change. Like the 256 word size, horrible design decision. Never should have been done. It was a stupid thing to do in the first place. And it kind of made sense at the time, but looking back on it, it was a bad design choice. So the thing is, not here to totally shit on the EVM. It's gotten me and everyone else very, very far. But I think for me, it's great to try something new, but I'm also very happy that there's people who are going to make it very performant and allow us to use it for a very long time. I think it's still a great system regardless.
Can you still be Ethereum aligned and not use the EVM?
I think so. I 100% think so. But I think that is, I think all Ethereum aligned really means is that in your, token plans, there's a bunch of Ethereum people involved, I don't think it's real. So I think that there's a lot of people, and this is coming from an ETH maxi, okay? I am 100% from the day an ETH maxi, okay? But, I am not quite happy with what's going on around here, this alignment thing. I think that Ethereum is about values, and it's about a community, and it's about being weird and cypherpunky and trying to create a sort of escape hatch for society financially so that we can do other kinds of things and not have all the financial engineering of the world done by a bunch of Wall Streeters, So that's why Ethereum is important. It's not about the virtual machine or the language and all that stuff by any means. Yeah.
All right. And Misha was going to hop on the Ethereum alignment meme. I'd like to do so in the frame of the sharding roadmap and the transition to now this roll-up-centric roadmap. Why the transition, in your opinion, and what does alignment mean in this new paradigm?
Okay, it's like alignment talks, huh? All right, let's just skip the alignment talks for now. It's like alignment talks, right? It's like alignment talks would be relevant if there is some major ETH podcaster among us. It's like there is no one like this. Okay, we're skipping it. So it's like then we're going forward. Yeah, I'm talking about like a very particular one actually. Whatever. It's like no offense. So all right. So effectively, what's the initial idea like for sharding, right? It's like the initial idea for sharding for ETH was about bringing horizontal scalability to ETH. So it's like so you could scale ETH not by increasing the the throughput of one particular machine, making it super server like Solana does, right? Or like I don't know, like guys on your side, is it it's like vertical scaling, right? I mean effectively, yeah. But to introduce more and more machines, it's like maybe not that large ones, maybe like cheaper ones, but to be able to parallelize the execution across that. So that's the differences. So effectively, what we are arguing about is like guys on one side, me on another side, is effectively vertical versus horizontal scaling. It's like I'm standing on the horizontal scaling side. It's like Ethereum once upon a time also stood on a horizontal scaling side, and I mean this would have been quite a nice addition to the protocol. Let's say this way, it's not known which particular properties in terms of development experience it would have brought to us, but the fact that this would have required to introduce upgrade to the protocol, which held quite a lot of value back then already, and now it's became even worse. So it's like introduce such a massive upgrade to the protocol, which would induce kind of very complicated function and scenarios. It's like it simply just got stuck in development hell. So and since back then it's like no separation of the execution layer and the consensus layer happened, it wasn't possible to introduce such a horizontal scale into ETH without upgrading the protocol. Now, since this execution layer and consensus layer separation happened effectively, there is a way to plug this in. It's like kind of plug this in, but yeah. And since the PBS also happened, there's also the way to plug this into the whole Ethereum system without upgrading the protocol, because it's not that monolithic yet. It's like it has become composable out of different things. It's like builders, proposers, like effectively sequencers, right? It's like sequencers, proposers, perfect. It's like that's the one layer. Another layer, okay, execution layer, different layer, like a third layer, like consensus layer, perfect. So in this architecture, you can plug yourself in without upgrading the protocol. So this is effectively like bringing horizontal scalability to ETH. That's what it is. So I mean, that's why it was canceled before, and that's why it became possible to be done right now, and that's why we're kind of bringing it.
So why can't we have both? Vertical scalability as well as horizontal scalability.
Vertical scalability is effectively on our side is increasing the throughput of a single shard. It's making single shard more and more performant. It's like, sure, I mean, it makes sense to be done. It's like if you're looking to running everything on top of a single shard. It's like, I would say that for practical purposes, there are certain limits up to which limit it makes sense. It's like, so we kind of resulted into for now at least, just simply decreasing the replication interval, like to whatever, like Arbitrum has, Arbitrum for example, made it like 0.25 seconds or something. So it's like we decided to stop at 0.5 for now. It's like we'll see how it goes. We'll see how it goes next, and just to focus to scale it horizontally. So you can do it for sure. I mean, it's like it just makes it more complicated. There is also it's like another nuance about this. It's like it's like introducing the parallel execution to the EVM itself, the virtual machine itself, at a sharding level, considering that you need to prove those shards to ETH to borrow the security to effectively be the Ethereum extension, right? So to be as secure as ETH. This introduces a lot of complications in terms of what you need to prove. It's like the complexity of what you need to prove. It's like it turns out to be just tremendous. It's just tremendous. You gotta effectively go through all of the optimistic execution phases. You gotta predict them. You gotta make a circuit for that, and this makes the execution less predictable. It's like, and we want to keep it deterministic. We want to keep it solid, as Ethereum is right now. So we want to keep it in the same time provable. So this way, it seems to be it's provable. You can still be secure. You can still be solid, but in the same time, I mean, yes, I mean it's kind of trade-off.
I would just say, in terms of rollups themselves and why it's so valuable for Ethereum, it's because the model we had before was rely on Vitalik and the Ethereum Foundation to do everything. And quite frankly, that was not a very sustainable model, as we found out over the years. And basically, rollups allow a lot more creativity from an infrastructure level. And rollups and all of the different pieces, shared sequencing, all the way down to different kinds of infrastructure, while they introduce a lot of complexity, it's not fun by any means. It also allows for a lot more creativity. And similar to how the internet's built, where initially it was probably just a few computers, and if you had asked a guy in the early 90s, like, hey, how's the internet built? He would have said, well, I just run this computer and people connect to it and it's done. And you're like, yeah, but what about networking? What about overwhelming the system? He's like, no, that probably won't happen, and eventually you break out each compartment of the system. You say, this is a device for networking, this is a device for, different kinds of storage, and you start breaking out the different pieces. And that kind of thing is happening right now with Ethereum, where we're realizing what Ethereum's good at, what kind of piece that can fit in a bigger puzzle, and what kinds of things we can break out into other systems, And I think that while you can go and just build another layer 1. And this solves a lot of problems, don't get me wrong. It solves an enormous amount of issues that Ethereum currently has. And you can use new kinds of consensus, you can clean it up, probably use Tendermint, because in the end, everything comes back to Tendermint. Basically,
we actually don't use Tendermint.
that's fine. I'm just saying, you'll get there. Don't worry. You'll come around. You know, I'll be waiting for you.
Okay.
The main thing is that this process is good because we're trying to understand which pieces fit where, or what their purpose is. And rollups give us another level of creativity that we didn't have before. We had to wait for the EF to add an opcode. I waited many years, many years for several opcodes. Like push 0, that was a many-year wait for me. So instead of waiting, now we can just do what we want to do. But we can gain the benefits of Ethereum, the liquidity and everything else. So it's really nice, it's very expressive, and it's really creative, and it's why I think Ethereum will always beat some other layer 1, which I won't mention, because it's more creative and it's more expressive at the infrastructure level, which is very cool, yeah.
I just wanted to mention one thing, which is that I think it's possible to be Ethereum aligned by doing fundamental research that's useful to the Ethereum community and then contribute that research back to Ethereum. And basically by going in a direction that was unexplored and that has turned out to be actually really important to scaling the EVM and scaling Ethereum, there's a path forward where folks who are doing fundamental research, for example, like addressing this problem of making Merkle tree state access much more efficient, or implementing optimistic parallel execution. Like these are improvements that now we see that we need for Ethereum, and so there are other ways to be Ethereum aligned beyond just purchasing data availability from Ethereum, which is ultimately going to be kind of like the business model for Ethereum.
Is the end goal then to embed that into Ethereum itself? If the research is done on this layer 2, if you will, some other execution environment, if that's the experiment, that's the research, is the contribution to Ethereum doing it at all, or is there an inclination that it'll get accepted into the Ethereum protocol?
Yeah, it's not up to me whether any improvement gets accepted into the Ethereum protocol, but what I can do is make EIPs, propose improvements, and yeah, just contribute back to the space. That's our intention.
Got it. Okay.
It's going to be a lot of work,
Oh,
just
yeah.
to be clear. Like any integration, you know, it's a different system, but also proving it out, proving that it's possible, proving that it can stand up to the real demand of very high throughput transactions with many users. I think that needs to be proven out, but once the capability is proven, then that's a strong motivator to start incorporating things into Ethereum itself.
Awesome. Yeah, I think this is pointing to modularity as a concept, as this experimentation layer, where a lot of research can happen and you can contribute that to the Ethereum mindshare. So, I'm still curious about Tendermint. I mean, is it only a matter of time?
You're talking about like just people building more Tendermint chains, or you mean what specifically?
Yeah, the Tendermint consensus.
Well, here's my hot, spicy take, which maybe some people in the room like and some people don't, but I think that a lot of different people do a lot of different things with consensus algorithms. And there's like, if you research consensus algorithms and blockchains, you'll find thousands of papers. Everyone thought they have a great idea, a really great consensus idea. But if you really want to know what someone who's been here way too long thinks, I think that a lot of things just end up back where Tendermint is. And basically, it's very hard to get past that because Tendermint's very straightforward, it's very simple, and it also accomplishes the real goals of proof of stake, in my opinion, in a really elegant, simple way. And so proof of stake right now for Ethereum, like it had this very expansive design with like all kinds of validators and like this really immense set of validators that they thought would be, posting everything. And now Vitalik's starting to realize, well, wait a second, maybe that wasn't so good of an idea. Or maybe we don't need all these people. Maybe we just need 8,192 validators. And that number smells awfully familiar to reading the theoretical limits of Tendermint's maximum validator count, which is around 10,000. So basically, in my view, my spicy hot take view, whatever you think of him, Keone was quite right, and I think that basically Tendermint has a lot of potential in the future, because I think there's a lot of interesting new expressive layer 1 designs, and Tendermint can fit really nicely inside of those. But you know, I'm no expert. I'm a user of these things. But yeah, that's my spicy hot take.
I think if Tendermint can support 8,192 nodes with a fully globally decentralized network, then you know, I would be happy to utilize that. But I think from what I've seen, all of the Tendermint chains cap out at about 100 nodes, which is not enough in my opinion.
Yeah, I mean, I think that's
Or they co-locate them. They put all the nodes in the same region, which is super annoying also.
yes, I think the current implementations of Tendermint, quite frankly, don't really meet, I think, what its potential is. And I feel like as well, at the end of the day, there's a lot of optimizations that haven't even been done yet with Comet BFT and other architectures, so yet to be seen. But you're right, like, while it's in theory, and that's what's in the papers, and that's what's theoretically, you know, surmised, in reality, it's a much lower validator count. Now, mind you, there's good reasons to have even a lower validator count, quite frankly. But I think that what Ethereum gets right in terms of consensus is just the fact that BLS does help us with the communication congestion of lots of validators, and I think there's going to be a great storm coming of BLS that meets Tendermint in such an incredible way. And so for me, I'm very excited for the future of what that's going to mean. But you know, again, I'm just a humble user of consensus systems, so I'm not making one myself that anyone knows of. So, yeah.
Alpha.
Yeah.
I think we're at time. Round of applause for all of our panelists. That was fun.